Hello there, students. Today we're going to do a little wrap-up of our light lab and lead you into the tail end of it. As we go along, pause after each lab section to make sure that you've taken good notes and you've answered all the questions thoroughly. So starting with Station A, even if you didn't begin there, start there because your paper starts there. What did we learn from Station A? Well, we saw some evidence for the law of reflection. And the law of reflection states that the incident angle, that's the incoming angle of a light ray, is equal to the reflected angle of that ray of light. Our evidence is what we saw in the lab activity. In the lab, we fired that beam of light right at a flat mirror and bounced it off, and we used a protractor to measure those two angles. There's a video link in Google Classroom that you can check out if you missed that part of the activity or you'd like to re-see it again. Those two angles, angles of incidence and angle of reflection, are exactly equal if done in a perfect setup. Now, we may have been off by a degree or two because we were using a dry erase marker on a dry erase board and measuring with a protractor. Not the most exact set of tools ever, but those two are equal under great conditions. Station B, well, what we learned here had to do with how light behaves on curved mirrors. And we see that the law of reflection is obeyed on curved surfaces. Take a look at this first mirror we saw, the concave mirror. In the concave mirror, all of the light went in and was focused to one small point. If you follow any one of those beams of light, any one of those rays, it's reflecting off of the surface of the mirror exactly the same way it did off of the flat mirror. It's just that as the curve changes, the direction of that reflection changes. Our evidence with the convex mirror is very similar. The light moving in bounced off and scattered outward, but it followed a very predictable pattern, as if that curve were a series of flat mirrors all aligned side by side, like on a disco ball. So we can see that law of reflection is still held true on concave and convex mirrors. Now there's a follow-up question there. Where do we use those sorts of mirrors outside of science? Well, I thought I'd show you some of the real-world examples you may have run into. If you've ever used a mirror that will let you look at your face very, very closely, which I don't recommend, you've used a convex mirror. The same thing is true if you've ever been to a convenience store and noticed up in the corner there's a convex mirror. This is so that the cashier can see a wide angle of light gathered and focused in a straight beam back to the cashier. This allows the cashier to look up and down the aisles without having to leave the register. Keeps an eye on shoplifting. As for a concave mirror, I want to show you an example that's a mirror that doesn't reflect visible light. This is a satellite dish, and it gathers light in the form of radio and microwaves, and it focuses that light down to that small collector sticking out in front of the dish. It's a concave mirror, just not a mirror that's reflecting visible light. Remember, all light is energy traveling as transverse, non-mechanical waves at 300 million meters per second. It's all the same stuff. Now in Station C, what did we learn there? We learned about refraction. And refraction is when light bends as it passes from one medium to another. We observed this in a lot of things that we saw in the lab. One of the first places we saw refraction was from this block. You notice the beam of light moves in, and as it enters the block, it changes angle slightly. As it travels through the block, it goes in a straight line, but then it changes angle again as it goes from the block to the air. Every time light travels from one medium to another, it changes its angle. Because the two sides of the block are parallel to each other, the two beams of light, the incident and the refracted or exiting beam of light, are parallel to each other, but they don't line up with each other. They're clearly offset a little bit. The other thing we learned at Station C was that white light is a blend of several colors. And we made this happen. We made this happen by refraction. As the white light enters our prism, it bends at one surface. As that light moves through the prism, it starts to separate into the individual colors that make up white light. It does this because the light hitting that angle separates the light by its wavelength. The higher energy wavelengths at the bottom and the lower energy, longer wavelengths at the top. They separate even further as they bend one more time, leaving the glass prism and moving into the air. Now, if we wanted to extend this a little further, we could do what Isaac Newton did, and we could take a second prism and put it in front of just one of those colors. And we'd notice that, let's say we put it in front of the red, that the red light wouldn't divide any further. This is some evidence that the prism is dividing light rather than changing it into something else. If the red enters as red and leaves as red, then that's all there was to begin with. Since the white light enters as white and then leaves as other colors, it's clearly a blend of those. Be sure you've paused and are writing these things down. If you haven't now, pause. Make sure your answers to sections A, B, and C are very thorough. At Station D, we continued some refraction. The goal here was to take a look at some refraction that happens somewhere other than just with your standard lenses. Some evidence of what we saw in the lab of refraction was the the marker in this case, that was in our beaker of water. We could see that it wasn't clearly lined up. We also saw how light traveling through calcite divided an image into two individual views. In the case of the glass of water, the straw isn't really broken. The light from the straw gets divided into two paths. The path that's at the top doesn't get refracted by water as it passes through. The light at the bottom gets refracted and bent as it passes through the water and then out into the air. The same thing is true if you've ever tried to look at fish in an aquarium. If you look at them from the top or the side or the front of the aquarium, you're going to see the fish appearing in very different places. The fish may not necessarily be jumping from place to place. It's really just your angle of light traveling from the object to your eyes. In this drawing, when you look into the water, you see where the fish would be in a straight line in front of you. Your eyes make an image there, even though the fish is actually lower and the light has bent, leaving it going towards your face. Pause and make sure you've got some thorough answers for refraction. Station E was all about color. The big thing we learned from this station is that we see objects when they reflect a color to our eyes. Any other colors that hit that material get absorbed rather than reflected back to your eyes. And we set this activity up to match some of the things that we observe in our regular daily life. If you're wearing a blue shirt, it looks blue because blue light bounces off of it and travels to the eyes of the observer. Any other color that hits the shirt gets absorbed. You don't see that color, those absorbed colors, because they never make it to your eyes. You only see the colors that have bounced off of the material. In our experiment, in the green light, the red plastic didn't reflect any red back at you. The light actually looked kind of a yellowish. Any of the yellow from that light bulb that was mixed in with the green was able to be reflected from the plastic, but not the green. In the red light, the green plastic didn't look green. It had no green to reflect back to you, so it didn't look green in those cases. Be sure you've paused. You ready to move forward? Now, Station F. What did we learn? We learned here that light is energy. We revisited the radiometer that we saw in our thermal unit. And in our thermal unit, we learned that darker materials absorb energy better, and that lighter materials tend to reflect energy. Our evidence for this in the lab was seen with the incandescent bulb, more so than with the LED. The LED didn't give off much light at all. The LED bulb is the one that's in your your cell phone. The flashlight had the incandescent bulb. Our evidence is that the sails always spun as if pushed from the dark side of the radiometer. That meant energy was being absorbed on that side. The lighter side of the radiometer was reflecting away light. Now the sails would only spin with that older style light bulb. It's a good indicator that's giving off more energy. Maybe it's giving off visible light and infrared, whereas the LED is probably giving off mostly visible light. It's one of the advantages of an LED, is it doesn't waste any energy being turned into anything other than the light we want.